Cool. Good morning, everyone. So my name is Bhargav. Bhargav Srinivasa Desikan is my full name. You can just call me Gav because my name's really massive. What we're going to be doing today is text analysis. I will be doing more of a breadth kind of thing than a depth. So I'm going to introduce you all to a really large variety of tools which you can use in the context of Python and text analysis, so that you can all go home or go wherever and then actually do these things on your own laptops, or whatever machines you're using. So the idea is to kind of allow everyone to be able to do all of these cool things outside of this tutorial as well, and also to understand what kind of tools are available. Because I think what happens, especially in data analysis in general, but also in text analysis, is that you're kind of overwhelmed with all the different kinds of tools, and you're not sure where to start, what does what exactly, and where do I get data, what's even going on. So I'm going to try and streamline this process for you a little bit, make people aware of the kind of things you can do and how you're going to go about doing it. And that's going to be the general theme of this tutorial. A few things before we actually get started. How many of you all have installed all the requirements or set up a Jupyter Anaconda or a virtual environment or something? Can I have a hands up briefly for those who have? OK, that is very cool. So I understand there are some people who might not have this set up. And while it would be ideal to have this set up, for the purpose of this tutorial, I'm going to be walking you all through a Jupyter notebook. And we're going to be going through that. But that being said, there's a lot of information in this tutorial. So the only real thing you all will be doing is pressing Shift-Enter at each Jupyter cell, which is not a lot. I mean, there are, of course, a few things like looking at the contents of a particular list or something, which I will also be doing on my own Jupyter notebook. But the point of me saying this is if you somehow could not have got your entire setup ready, it is OK. It is not a huge problem. What I would need you to do is you should have also got an email yesterday if you were signed up for the tutorials, with the link to the GitHub repository, which has my code. If you don't, I'm going to just show you this briefly. It's really OK, you can search up. I'm just going to write this down if you don't have it. But it's Bhargav Vader, which is my first name, and like Darth Vader, like VADR after that. So it's Bhargav Vader. This is my personal GitHub repository, and it's /personal. So if you just go to github.com /Bhargav Vader /personal, yeah? I could do that, definitely. I think I can. Hold on. Sorry. Apparently, OK, hold on. I'm not sure how to make zoom in on using. Oh, there we go. Cool. Oh, yeah, sure. Hold on. I'm just going to try that again. Oh, neat. Wow, I couldn't have done that. OK. So, yeah. OK. So please, yeah, you're also more than welcome to keep stopping me if you have any problems with regard to how it's being done or if I'm not saying something clearly. Basically, to find this tutorial, you'd want to go to github.com /Bhargavator /personal /notebooks over here. I actually sent this link over yesterday. In case you do not have this link, let's just take a second, if you do not have all of this set up, to go over here and find this. So you'd want to go to text analysis tutorial. And in the README, I talk about what you would all be needing. So I'm going to spend around 5 minutes to just kind of find this particular page. If there are any problems in finding this page, please put your hand up, and I'll get you to find it. So again, it's github.com /Bhargavator /personal, then notebooks and text analysis tutorial. So ideally, if you would have got this and downloaded and had like your environment set up, that would be really, really great. I've also given instructions on how to do this. It's basically setting up a virtual environment and downloading using pip or whatever you would like to use from the requirements file, and then running the Jupyter notebook. If anyone needs any help with regard to this, I'm over here. I'm just going to give. So it's 11:05. I'm waiting till 11:10 to kind of get people over here. So I'll just give 5 minutes for everyone to find this. Also, just to note that even if you cannot find this, I will be running all of these notebooks on my machine, and you'll be able to see all of that, and I will be talking about it. It's just going to be a lot easier if you also have it in front of your computer. And I will also be talking about, like, I would encourage you folks to all try out different Jupyter cells if it needs to be done. But that, yeah? Okay, cool. I was just saying that you don't absolutely need this page. It'll just be very useful. Sure.
One of your instructions is to install virtualenv and what version of Python are you expecting?
So it's a Python. It's Python 3, 3.5, 3.6. I've got to check. But that being said, I mean, you can use Python 2 for this tutorial as well. If you do, then I have a few code snippets you'd probably need to use because of the Unicode. And because we're dealing with textual data, so of course we need to be very clear about the Unicode part. But apart from that, you could use Python 2, Python 3. You don't even need a virtual environment. That was just what I use. Or you can use PyEnv, Anacondas, whatever you want. You can use anything. It's just mine would be on Python with Python 3. Another note is if you all plan to install all the requirements right now, it might take some time because Spacey has a language model, which is I think like 45 MB, or like depending on what size, it might take some time. In which case, I mean, you could probably have it running on in the background, the installation, but again, I would like to make it clear it's not absolutely necessary for you to all get something out of this tutorial. Though it would be very, very nice if it's installed so that when you have time to go through this on your own, you can. So the Spacey language model, which I will talk about in detail, of course, but I have a link over there which talks about it and how to do it. And these are the Python packages we'll be using: Jupyter for running the notebook, Gensim for topic modeling, Matplotlib for plotting, Spacey for other text analysis, and some visualizations. Yeah? Yeah, so there's, no. So I've mentioned that over here. Requirements _1 is the one for text analysis, which should have Jupyter, Gensim. So there are 2 tutorials in this. So you have topic modeling and you have text analysis. We will be doing text analysis. So I believe that the requirements _1 file has the ones for the tutorial we'll be doing. No problem. Cool. It's 11:10, so I'm going to start. Again, just a note, because I realize there's a lot of installations and a lot of things you might want to set up. It would be very, very nice if you could all spend some time after the tutorial or during the time of the conference to actually install all the things I've talked about here, because they're going to allow you to do this on your own, of course, so that you're not just stuck to what I'm going to be talking about in this tutorial. But if there are problems with installations and things like that starting right now, I will not be talking about those right away, because I will be spending the rest of the time to actually talk about the tutorial. So are there any questions before I start? Any problems? Is everything OK? Awesome. So this is going to zoom in. Is this OK? Can everyone see this? Or is the perfect level of zoom? Yeah? Cool. Awesome. So we're going to be doing text analysis. Text analysis is data analysis where our data is text. Now, what I personally find very neat about text analysis is that it's very easy to actually get this data. And it can also be personal and things that you care about. I find sometimes when you do generic data analysis, you might get kind of lost in the numbers. They're not very interested in what you're trying to do. Like the more common data set is, I think, the Boston housing data set for regression, which is kind of boring, predicting the prices. There's the Iris data set, which is, again, not super fun. So for me, what I personally like about text analysis is I can use whatever text I want to. You can pick up tweets. You can actually, if you have legally bought PDFs, you can analyze those. You can analyze whatever kind of textual data you want. Newspaper articles are a bunch of fun. I used to use the messaging WhatsApp app a lot back in Asia and Europe. So I used to actually analyze my own textual conversations, which I used to have with my buddies. And that was also a lot of fun. And the point of me saying this is that text analysis, one of the huge parts about why it's interesting is the fact that you can actually use personal data to get insights into what you're using. It's also used a lot, of course, in industry by a lot of people trying to figure out like advertisements, so on and so forth. You have chatbots, which is also a part of text analysis. So there's a lot of generally cool stuff you can do using text analysis and text. So that's why I'll be talking about that in particular. Now, the idea, again, like I talked about before, is breadth and not depth. So I will be talking about something called computational linguistics, which is basically making computers deal with linguistics. So you have things like parts of speech, right, like nouns and verbs and so on. How do you write computer code to identify nouns and verbs in a sentence and in paragraphs and so on? That is one part of what I'll be talking about. Then there's topic modeling. Topic modeling is if you have lots of large text and it's completely disorganized, how can I find underlying topics? Like if it's newspapers, how do I find like a sports topic, a politics topic? How can I find this from text? How do I classify text into different categories? I've already found out for myself, like spam or not spam, which everyone here uses email, I suppose. So most people here would be using email. So you'd have spam and not spam. This is text classification. Then you also have text generation, which is like what chatbots are doing. Right? You're kind of having a conversation or talking, so to say, with an algorithm which generates something resembling human speech. So there's a whole wide spectrum of really cool things you can do with text analysis. And we'll actually be very briefly going to do all the things I just talked about. It's going to be kind of fast. That being said, questions are totally welcome and awesome. So please keep stopping me if something is not clear. And well, let's get started. So what would be ideal is if everyone had this particular Jupyter notebook open on Jupyter. But if not, then we're just going to be watching me press Shift-Enter instead of doing it yourself briefly. So the first part about text analysis is usually, of course, finding your textual data. So that's what we're going to be starting with. I'm going to get my import set up. Very briefly going over the imports we're using or the packages we're using. Gensim is for topic modeling, which is on top. NumPy is, I suppose most people here would know NumPy, but it's a way we store our numbers in using Python in forms of arrays, which are used, again, in data analysis a lot. You have Spacey, which is a package I really, really like, which does industry-grade natural language processing. A lot of people, when they think of natural language processing in Python, think of NLTK. NLTK is quite outdated, bloated academic code and is OK for teaching or learning NLP stuff or computational linguistics. But for anything practical, if you want to do really cool projects or even anything, Spacey can actually be used in your production level code. So we want things to be practical, so we will be using Spacey. That being said, NLTK can be useful for learning about natural language processing. Then we have Matplotlib to plot stuff. Scikit-learn is a machine learning library which we'll be using for classification, which I talked about before. This is to just briefly introduce Scikit-learn in the context of textual analysis. And then we have Keras, which is a deep learning library, which is a kind of machine learning where we're going to be dealing with neural networks and generating text. So these are the libraries we're going to be using today. And I've just set up the imports. Then we have warnings and OS just for some other stuff. Then we're going to start with gathering data. Now, I talked about earlier why I like textual analysis, because I can get my data from anywhere. And when I started doing this tutorial, I started doing the whole gathering data part. I wrote code to go on Twitter and scrape Twitter data, which is always interesting because it's super relevant, right? But now the thing is that takes a lot of time and effort and ended up becoming a tutorial of its own, which I could not fit into this. So Well, I would love to talk about it if any of you want to after this. For this tutorial for the text, we will be using a built-in data set which comes with GenSim called the Lee background corpus. It's basically 300 newspaper articles from an Australian newspaper broadcasting agency. So the context is Australian news, early 2000, which is not super exciting, but it's very easy to get. So it's what we're going to be using for the purposes of this tutorial. And something called the 20NG data set, which stands for 20 news groups, which is basically a massive newspaper. So the theme is newspaper articles because it's kind of easy to understand and play with. But what would be ideal is to have some data which would, of course, based on either your business model or whatever, or if it's on something personal, it's a lot more fun. For the purpose of this, we'll be using early 2000 newspaper articles. And how we're going to be getting this data is, well, the first 3 lines of code over here, which is actually on the GenSim website. We're basically loading our test data from where we've installed GenSim. So what's happening over here is doing os.sep and using the GenSim path, we'll be basically accessing the data. So now our file, which is called text, contains all of our newspaper data. Now, this is a huge, cleaning data in general is a huge, huge problem or thing you have to deal with in all kinds of data analysis. But in textual analysis, it kind of becomes even more important because, you've again heard this probably, or you should hear about this when it comes to data analysis, but garbage in, garbage out. If you're going to have rubbish data, you're probably going to get rubbish results. But again, what's important to know is that rubbish or garbage is very, very contextual. What is useful for one person might not be for the other. For example, numbers in data, in textual data, sometimes you might want to know what kind of numbers are coming up in our text. Sometimes you don't. So sometimes we keep in our numbers, sometimes we don't. Sometimes you want to keep in places. You don't really like verbs on Tuesdays, so that day I'm just not going to use verbs, right? So basically, there's a lot of different ways you can clean your data. And this is a huge part of textual analysis. And I often say that this is the most important part of the tutorial, the cleaning data part. After this, you could read the code, but after this, it's not as, this is very, very important is my point. And we will be using Spacy to do all of this. Now, the way Spacy works, and this is very important as we go on, Spacy has what you call language models, which based on your language, here we'll all be using English for the purposes of this tutorial, but you also have Spanish, German, Italian, French as pretty well-trained models available by Spacy, but the most popular ones are in English. Now, what these language models are statistically learned machine learning models which know what kind of words are verbs in certain contexts, which knows what kind of words are nouns, which knows what kind of words are numbers, and so on and so forth. So Spacy's language models knows what certain are stop words. Stop words are certain words which we use which we believe don't have information. Basically, Spacy has pre-trained models with a lot of rich linguistic information. This is very, very useful when we're cleaning our text, which you're going to be seeing right now. The way you load a language model after you download it, which are the instructions I've given you on the GitHub page, after you download your language model, you would load it with this line of code. It says NLP is equal to spacy.load en. En here is English. For Spanish, I think it would be ES, I believe. And once now that NLP dot variable is now our pipeline object, which basically when we can now pass text through this pipeline and start annotating our text and doing cool things with it. Now, I previously mentioned, I said the word stop words, but I did not really go into it. I'm going to briefly talk about what stop words are in the context of text analysis because it's very, very important. Stop words are words which normally don't provide any extra information during textual analysis. An example of this is, for example, if we want to figure out what kind of topics are coming up in newspapers, which is what we're going to be seeing in a bit as well, the word I or said or me or has, just certain words don't add much information. For example, if you want to know what the topics are, we don't want a nouns topic or to do with in general with pronouns or something. We'd rather have sports or politics or something which gives us more information. So stop words are words which do not provide us particular information in textual analysis, and we want to get rid of these words when we're generating our corpus, which we later play with. A corpus is the textual data set we will be using. So in this context, I've already done this experiment once before. And what I found out is that the word say or saying or variants of the word say comes up in newspapers a lot. Now this is not going to be useful information in a topic. If I don't know what is being talked about in between 2000 and 2001, and I just get say, said, Mr. Being, I'm like, that's not useful. So I know this having done the experiment once, and these words are not traditionally stop words. So I'm adding these words to my stop word list in these 4 lines of code over here. Now, spaCy already comes with its inbuilt a list of suggested stop words, but usually based on the context of your problem. If you're dealing with biomedical data, for example, and you think one word, a protein, or I mean, probably useful, but in the context of your experiment is not useful, you would want to add that word as not useful or to my stop words list before starting. I've included that here because later it would just because it saves time. But normally how you figure out what's not useful is you do the whole experiment and you look at it like, oh, that's not useful. And then you come back up and then you add this bit of code before you start, then you start again. But a huge part of textual analysis is this. You never get what you want the very first time. You kind of want to do things a whole bunch of times. I know that in the context of newspapers, these are not useful words. So I do this. What is going on here is for each particular stop word in my list of stop words, I'm using the pipeline and saying the vocabulary of stop words in that pipeline, make that true. So over here, this is actually standard spaCy code. This is how spaCy does. Here, a lexeme is a linguistic unit. And each word it's just the words which they use over here. But as you can see, we're basically getting the lexeme from the word and then just saying, is stop true? Yeah, it is a stop word. So this is just a small, before we actually get started with what's going to happen, what stop words are. Is it clear what stop words are? Are there any questions about stop words or why they're important? No? OK, cool. So now this is very important over here. Our 6th line of code, I'm doing doc is equal to NLP of text.lower. So NLP, if you'd remember, just 2 Jupyter cells up, is spaCy.loader contains my English pipeline. I am now passing my document through the spaCy pipeline. Again, what is my document? Just remind you all, in the context of this, it's my text which I've opened, which is the newspaper articles. So when I run this over here, which is going to take a small time, but not too long, it's basically annotating every single word in my corpus, which is all those newspaper articles. So it's going to know in all the Australian newspaper articles, the details of every single word in it, which you're going to see very briefly here. So now I'm going to show you what doc is. So you can see it says it's just text. It just looks like text right now. But hundreds of people have been forced to vacate their homes in the southern highlands of New South Wales, a strong wind. So it's like a fire, and they're talking about this fire in New South Wales in the year 2000. And so there's a lot of different articles. And now all of these, which you cannot see right now, but I'm going to show you really soon, all of this has been annotated by spaCy. So now the doc object contains information of every single words. Is it a stop word? Is it a number? What's its part of speech? A whole lot of information. This information starts becoming very useful a little later, especially when you're cleaning text. But in general, it's just useful to know when you're doing any kind of textual analysis. You're going to see exactly how briefly, but this is what you need to know right now. Again, is everyone clear what we're doing or why we're doing what we're doing? Yeah? Cool. So now I want all of you to remember that, but temporarily we're going to go out of context to show you what exactly computational linguistics is. So when I did that, when I basically said document is equal to NLP of something, it annotated everything. Now, I don't want to show you all examples based on that massive text. So I'm going to annotate one sentence and give examples based on this. This particular subfield of text analysis is called computational linguistics, which is kind of separate from natural language processing in the sense that you're dealing more with linguistics or structures of sentences and language, right? So we're going to now run a sentence to the same pipeline we ran our entire corpus. The sentence is, oh, it's Tom in Turkey to get some of those delicious Swedish meatballs. And now I'm going to go over some basic things you can do with spaCy. So the first is part of speech tagging or pause tagging. What we're going to do is we're going to now show you what parts of speech are here. So for token in sent. Again, for context, sent is basically that particular sentence after it's gone through the English language pipeline, right? So I'm running this over here, and it very, very quickly, it shows me Tom is a proper noun, went is a verb, to IKEA a proper noun to get some of those, delicious is an adjective, Swedish adjective. So you see what's going on here. Spacey now knows what all the information in that sentence and gives this to you. Spacey also gave you all this information about that massive document before, right? This is just for this particular sentence. So you can go for every single token. Here, a token is a single individual linguistic unit of a sentence, and it gives you information. This is part of speech tagging. There's other things you can do. For example, NER tagging. NER stands for named entity recognition, which, as it suggests, it looks for specific named entities in our sentence. Over here, there's only 3 named entities. One is Tom, who's a person. It's IKEA, which is an organization. And you have Swedish, which over here is, so based on the context, this comes up differently. You can have political organization, country, place. So Spacey has you can go to linguistic features and look at what exactly, so over here, if you look at Spacey in terms of its named entity recognition, it has geopolitical unit, which is GPE. So you have a lot of different kinds of labels, like organizations. Then you have money as well. You have a lot of different things you can do with named entities. I would recommend searching it up based on what kind of named entity you would like to look for. But the common ones are person, time, place, and so on. You can also, here I went over every token in sentence, and I printed the entity for every token. Some of them don't even have them, like went and to. So if you want to skip all of that and just go through entities, you can do for ent, here ent is entity in sentence dot ents, and you can look up only the 3 entities which are here. You can also have it, Spacey has this really neat plugin called Displacey, which allows you to like visualize this in a pretty way. So over here, you just have this neat little purple thing over it. So as you can see, Spacey does a lot of cool stuff. Part of speech tagging is usually very useful in general text analysis. Finding out entities like this also pretty useful based on your problem. And again, I'd like to make it clear, like Spacey did this for that massive document too, right? Not just for this sentence. Now I'm going to show you what dependency parsing is, which is the idea that in a sentence, things are linked to each other in a certain way, like Tom went to Sweden. So it's like Tom, went is the verb. So there are things going on, right? So to find out these dependencies, I'm not going to get into the details of what these dependencies mean, because that's honestly a lecture on its own, like dependency parsing and parsing of textual data is a massive subfield of research. I just want to let you all know this exists, and Spacey does this for you. So this basically shows you the structure. Again, if you're more interested in dependency parsing, I would recommend searching up how Spacey does it. But to give you an idea of the kind of information, it's basically this. So it's like here, the root of the sentence is normally the verb for Spacey. So you have went being, it links, Tom. And so you can see that this is what Spacey does. It gives preposition, then subject, object. It basically tells you how a sentence is structured, right? You can get all this kind of information using Displacey and Spacey. And this is done sentence by sentence for every single sentence, which is why that took a little bit of time before when we were analyzing our doc. So NER, pos tagging, NER tagging, and dependency parsing tend to be 3 of the most important computational linguistic ideas, which are normally talked about or discussed. So is everyone here clear with what these 3 are, more or less? Yeah? Awesome. So you can, I would really recommend getting into, you also have this for Spanish, French, German as well. And Spacey is open source, of course, and is always updating its models to make them better. They're all neural networks under the hood, by the way, for those who are interested. It's a deep learning network which is trained to find out what exactly you would tag something as. You can also train your own taggers. So if you want to have like your own particular label or part of speech or whatever, you can train Spacey's models with your own data. So there's a lot of really cool things you can do over here in the computational linguistics part of spaCy. Now we're going to, so that was a small detour just to let you all know what spaCy can do. If you remember, the last thing which we had done before we took our detour is this doc object, which basically has all the Australian newspaper articles, right? So now let's go back to cleaning this, because there's still some kind of information which might not be useful to us. So now this is very important in the context of, so what we did before this was computational linguistics. Now we're slowly moving out of that realm into the machine learning part of this. And in machine learning, it means what's very important is vectors. Now the reason why vectors are important is machines don't understand words, so we need to represent them as numbers. And numbers, when there's a lot of them, and in text we have a lot of numbers, because, so I'm going to take, again, a super small detour. Is this, can I use this? So I'm going to try and explain to you how machines understand text in terms of data structures, right? There are many ways. Now let's assume that, again, these are hypothetical numbers, but they would be kind of close maybe. If we're going to look at a newspaper corpus, I can actually just look at the length of the dictionary in a bit, but let's assume that this, all the newspaper articles which we have, the 300 newspaper articles, if you look at all the different kinds of unique words being used in them, let's just say there are 10,000 words, right? So like all of the articles in these newspapers are only made from this vocabulary of 10,000 words. Now normally, of course, there's going to be a lot more words, but in the context of every machine learning, I mean every text analysis project we do, there's always a vocabulary, which is every unique word being used in your analysis. Now, how does a computer figure out what's in a document? It basically has this really, really massive like indexing of every single word. So if it's Tom, it would be like, you know, index 0, and then you'd have every word is index 1, running up to index 10,000 in vocabulary for each word, right? And then if you have a document, which could be even a sentence, it could be a document or whatever, it would basically have a 0 or a 1 based on if that particular word exists in that document. So you'd represent a document in a like each document, even if it has 3 words, would say 9,997 zeros and 3 ones, but you're still using up all of that data, right? I mean, you're using up all of that space. So this is why we have to be really careful in the best possible way we can give information to our models, right? So I'm going to be now talking about how we create our lists or list of lists to allow computers to actually use this textual data. Now, if all this sounds a little complicated, it'll become a lot more clear once I run these. I'm going to first just run this. Oh, this is a super important cell, by the way. Cell number 16 is very, very important because it's going to tell you how you're going to create your data structure, which is going to be your input for most machine learning algorithms. So this is the part. Let's go through this really slowly. So first, I create 2 lists. One is called text and one is called article. Text is basically going to be our entire data set or all our texts. An article is going to be each individual article. So for W in doc, doc, again, I would like to remind you, was that massive document, and W is every single word or token. So for W in doc, if the text or if the contents of that word is not a new line, is not a stop word, is not punctuation, and is not a number, I'd like that particular word to be appended to my article. Is that clear? That's basically this over here. So the reason I'm doing this is because when I want to create, for example, which I'm going to show you in a small bit, topic models or any kind of large statistical models, I don't want stop words. I know that. I don't want a new line because a new line in my data set represents a new article, so I want to keep it to one article. One article, if it's not a stop word, if it's not punctuation, like a full stop or a comma is not going to give me a lot of information about this particular topic, right? And if it's not a number, because in my context, I don't want numbers. You all could totally keep numbers if you'd like. If I have, and you could add more rules. If you're trying to create a database of only, like I talked about before, like only verbs, you could search for verbs and only put in verbs. So what spaCy does is spaCy now allows you to have is punct like number or not. And for example, if you want to find out what a verb is, I've talked about this briefly earlier, where it's token.pos underscore, where you would have verb or part. So you can choose what you want to keep in your corpus. I've decided to keep everything which is not a stop word, everything which is not a number, everything which is not punctuation or a new line as part of my corpus. And then after that, I've said, every time I do see a new line, I want to add that particular article to my text, right? So that's what's going on over here. To be clear what now our things look like, this is very important. What I've done is I've gone from this over here, right, which is hundreds of people have been forced to vacate their homes, blah, 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 to over this, where instead of hundreds of people have been forced to vacate, it's just 100 people forced to vacate home. Can you see what's happening over here? Like, this is very important. Cells 16 and 17 are very important because they talk about what cleaning textual data is. So remember what we've done before this, all the cells about this. You remember what I had, which is just like massive documents which have been annotated. And I've gone from that to this list of lists, where each list within this list is an article, and each list contains all the words which I think are useful. So over here, I got rid of like hundreds of people. You're seeing what's going on here, right? This is a very important part of text analysis, and is how computers are going to get anything meaningful out of what you say. So is this like 10,000% clear with everyone here? No hands up? Cool, I'm going on because this is very important, and the rest of the talk sort of builds on this, so it's important that this is clear. So just to make things even more clear, this would be only our first document, this would be only the 101st document, and if you'd want what is like, I don't even know if there's the 7th word in this document, which is important to us, is custody, must be someone's. So yeah, so this is to give you an idea of the kind of data structure we have. What is the size of this data? Sorry about that. So it's 299, which is 300. So this is just to give you an idea of the data set we are creating, right? Now we're going to move on. And I'm going to give you a little bit more information about the fancy kind of things we can do when we're cleaning up our documents. So we're going to introduce a topic called bigrams. Bigrams, I mean, it's n-grams. I'm going to be specifically talking about bigrams. N-grams are basically, you might have noticed earlier on when I looked at text, right? Just to give you an example, this is a really quick example. You can see New South Wales, right? These are 3 different words in my previous document. But New South Wales, I believe, is a territory in southern Australia. And so now what's going to happen over here is New South Wales is 3 separate words. But in our text analysis, it kind of would make more sense if it's 1 word, right? Because it means the same thing. If we see New York coming up again and again and again, we'd know that we'd want to rather deal with New York instead of New and York, and the same for Los Angeles. And so basically, any place where 2 words appear around each other so often they make more sense as 1 word than 2 words, then we'd want to do something called bigram generation. And we can use bigram, we can create bigrams with Gensim. You could also totally code up all of these things on your own, by the way, but these packages just makes things faster, right? So bigrams in the context of Gensim, which is the first machine learning package we'll be using, we're going to be loading it using gensim.models.phrases and texts. So we are basically passing all our text through this model, and I'm creating a bigram model. I'm going to now do the bigram part, which basically apply my bigram on line for every line in texts, right? So this is how I'm creating my text with bigrams. Let's see what it looks like. You can see over here, New South now has an underscore over there. It's New _ South. So this is what happened in that one line. Every instance of New South Wales, or it goes to that particular corpus. For the context of that corpus, do certain words appear around each other? If they do, let's make it 1 word. Now, of course, this doesn't mean that every time there's a new, the next word gets appended, right? It only means for this particular context, it gets appended. So you'll have different results based on what you're going to be doing. Rural fire and fire burn also got picked up over here, by the way. So there is a level of how much you want to be able to do this. If you want to make sure it's not picking up every word or what extent of it, you'd have to go into the phrases module and play with the parameters. which I'm going to leave all as an exercise because we don't have the time to do that. But based on your context, this can be very, very useful. Also, rural fire and urban fire, if they're different things, could also be useful. If these words are coming up together a lot, maybe they do mean something. So this is to introduce the idea of bigrams in text analysis.
When it comes to the place names like that, is it worth doing an entity extraction?
Sure. Oh yeah, okay. Totally. So like the question was, would it be worth doing a named entity recognition and then running a bigram to make sure you're only catching named entities? Yeah, totally. That would be a good way to do it, so that you're making sure that things like rural fire are not accidentally picked up. So you could run a bigram by, you could tag things as places and then make sure a bigram only does those places and go on and do it. So that is definitely a way you can go about doing things. Now, we still have to remember that in the end, even though we now have our data set in a more cleaned up, organized way with no stop words and some cool things put together, it's still words, right? And computers don't get words. So what we're going to be doing right now is converting words to numbers. And we're going to be doing a dictionary to do this. Now, a dictionary is a Python object dictionary. But in this particular context, it's a GenSim Python object called dictionary, which basically sets it up easier for you to do things. But the idea remains the same. Every word gets an ID, right? So we're going to be creating this dictionary using a dictionary over here is a GenSim module. So dictionary is equal to dictionary of text. So you're creating your dictionary from texts. And you're creating your corpus. In text analysis talk, corpus basically means your data set. It's just another word. For textual data, you just call it corpus in the context of any kind of textual analysis. Or even in the context of research, if you have like a corpus of historical Renaissance data, the word is corpus. This word comes up a lot in things you might be searching up later. So I'm going to run this, and I'm going to briefly show you what dictionary is. So it's a GenSim object, but you also, basically the index for 0 is near, and so on and so forth. So you have, based on the word, you have a different ID, and that's what dictionary is. And now what we're going to be doing is, let's check out the length of our dictionary. So there's 5,329 unique words being used. This is after we got rid of our stop words and a whole bunch of stuff, and after we combined words together and everything. So you'd probably have a lot more before you do the cleaning, which we did together.
I'm sorry, so the dictionary is, there's just a key, and then it's keyed to a word that has appeared in the corpus.
Sure.
Okay, so the dictionary was generated from the corpus, not like a larger list of vocabulary.
No. Yeah, I should have made that clear. So just to be absolutely clear with that, that's why we did dictionary is equal to dictionary of texts here, right? And text, if you remember, is just this massive list over here, which is all my newspaper articles, right? Is that clear?
Yeah.
So texts are all my newspaper articles, and dictionary of text is basically the dictionary of all the newspaper articles, which is all the unique words used there. But this is after we did the cleaning, right?
Yeah.
So no stop words. I'm going to show you right now. So corpus, the code says corpus is dictionary.doc to bow. Now I should probably explain that. Before that, I'm going to tell you what bow is. Bow is bag of words. So what's been happening over here, before if you had a document, like any kind of document, it would just be 0 or 1 based on the word being there or not being there. But again, that takes up a lot of space. What if instead we can do, it's probably going to be easier if I just run the code. Basically, corpus of 0, this is what text has become this 0, 1, 1, 1, 2, comma. What does this mean now? This basically means that the 0th word appeared once, the first word appeared once, and the third word appeared twice, and the 21st word appeared 3 times. Can you see what's going on? So the 21st word is?
The 21st word in the dictionary.
Yes. The 21st word in the dictionary is rain. So in that particular document, the word rain has appeared thrice. Now the reason we're doing this is because otherwise we would have this whole massive 10,000 word array with every single is it there or not, and we still so we want to compress that. So it's called a bag of words because each of these Each of the indexes is like a bag, and we're like counting words. So that's what's going on over here. This is just an easier way for the computer to deal with a sparse data, a sparse vector. So that is what corpus, and what is the code for that? Dictionary.doc2bow, so document to bag of words of text for each text in texts. So again, you could actually build this dictionary yourself by, it's not super fancy Python code, right? Like just iterate through all your documents. It's just a kind of a pain to do it. Gensim is specifically for text analysis and does it for you. To be clear, scikit-learn also does it spacey. Like any kind of Python text analysis library is going to have these functions in it. But I'm kind of breaking it down so you can also do the code yourself. But it's optimized, it's fast, it's easy, and dictionary.document2 backwards for text. So is that clear what we went to from where? Like we had this just raw text to cleaned raw text to list of lists of raw texts to bigram of raw text and now to a bag of words of raw text. And because this is kind of our final form of cleaning for our analysis, I'm going to call it corpus because that's just what we normally call in this particular field. So is everyone up to speed over here at this point? Awesome. Okay, so now we're going to start with, so until now it's 11:47, which means it's been 47 minutes, 37 minutes more or less of only cleaning text. The reason I've spent so much time is because it's extremely, extremely important. You cannot, even if you know all of these fancy machine learning methods after this, it's pointless. You're not going to get anything interesting or useful if you're not going to be very, very diligent with your text cleaning. So it's important to know what you can possibly do, why you're doing what you can possibly do, and have a sort of idea. These are not the only things you can do. There's a lot people get into more detail, and you can get, for example, you can get rid of words which are not frequent. Like if a certain word is just not, it's turning up once in one document, you're like, oh, yo, why do I even need that word, right? So you get rid of that, and you can keep 5 or 10 or whatever number you want as your minimum frequency cutoff. You can keep a maximum. If the same word's appearing in literally every document, is it information, so to say? So you can get rid of the most frequent words, the least frequent words. You can do all of these things. These are also things done in text cleaning. I'm not doing them because it's not necessary, but you can totally do it. There's a lot of ways to go about doing this. This is my way of going about doing this particular way. You get different kinds of results, but it's heavily contextual, right? Based on your business problem or whatever personal project you're working on, you'll be having a different cleaning process. These are the kind of stuff which everyone does. I have one thing to mention which I actually forgot to talk about. Over here, this is the super important one, number 16, that Giselle is talking about, right? I said article.append is equal to w.lemma, right? And lemma is not text. And I've written on top, we add the lemmatized version of the word as a comment over here. I forgot to talk about what lemmatization is. It's a very important part of text analysis. Basically, the word saying, said, and say, for example, all of them have the root word say, right? Or like writing, wrote, write, all of these have the same root word. So if this word appears in different, like because of the function of the kind of word it is, it appears in different forms in my text, it all means the same thing. If I want to capture that original root word, that's called a lemma. And this form of getting the root word is called lemmatization. So for some words, the word itself is the lemma, right? But for any other words, like saying will become say, and say is also say, but both of these represent the same word. It's called lemmatization. I would recommend you could do a really quick Google for lemmatization if you want to read about it. There's another concept called stemming, where you just kind of hack off the last part of the word. So like everything, but then it looks kind of ugly and it's not very pretty. So I prefer to use lemmatization. But you could also use stemming. Stemming and lemmatization are two ways in which we basically, if there are a lot of words which could mean the same thing, but are just different forms of the word, we want to just use that base form. That process is called lemmatization. I've also only added the lemmatized forms of the words. This gives better results. Though that being said, you could also not do this. It's really up to you. But this is a very important part which I missed out on. So it's the lemma and lemmatization, which also Spacey's got, like when it did its whole document analysis, it did lemma as well. So like, Spacey are not paying me, by the way. I really just like them. So we're going to start with topic modeling now, which is the first machine learning part of this tutorial, right? So I briefly talked about topic modeling before, very briefly. I said that if I have a newspaper corpus, which you happen to have, this is in a context of Australian, Southern, whatever. But let's just say very broadly, if I have a lot of textual data and I want to classify this and I have no information whatsoever, a topic model is a really nice way to get a cursory glance at my documents. For example, if I feed in 10,000 newspaper articles, I can end up, and I say 4 topics or 3 topics or something like that, I can end up getting 3 topics, which should be sports, which should have football, soccer, basketball, baseball, so on, and maybe some names, and politics, and you'd have certain names associated with politics, and weather, which would be sunny, beach, so, you know, or I'm from Chicago, so rain, cold, miserable. So you'd have things like this based on your newspaper articles, which you're actually dealing with. Now, we're going to find out so the way it does this is, it's called latent derelict allocation is the name of the algorithm. This is the name of the most popular one. There are multiple topic modeling algorithms that you can use, but it's called latent derelict allocation because these topics are not clear to us immediately. They're latent topics hidden under the text, so to say. Derelict is a kind of a probabilistic distribution, which is how it does it, which is it's kind of Bayesian inference. It's a statistical modeling algorithm where it looks at what kind of words appear around each other with what probabilities, and it kind of does an analysis of trying to find topics of words and documents which come together. Topic modeling in itself is a huge research field. I've done a few tutorials on topic modeling before, which you can search up if you're interested, or you can just talk to me after this. But I'm going to very briefly go through what it is. Rough idea, massive, unordered, unclassified text. Now you have topics, after which you can choose to classify or not classify. But these topic models are useful in general, right? So so I'm going to be, the import here is LDA model, which you can see over here, which is from Gensim, which if you check the imports, you would find it over there. What are my inputs or the parameters over here? Corpus is the corpus we just created. Number of topics, 10. So you have to specify, right, the number of topics you want. This is very important. It's not going to find out the number of topics on its own. There are certain algorithms which attempt to do this, but really you should have a very rough idea. Alternatively, you can just run like 7, hey, this makes sense, 8, this doesn't, and you can figure it out. There are more quantitative methods to find out the number of topics, but that's like a whole, again, field on its own. I've written tutorials about that in the same repository, which you can actually search up since you don't have this repository. I get more into topic modeling, but the idea is you need to tell the number of topics you'd want, right? So number of topics is 10, and ID to word is dictionary. Over here, it basically means ID to word, which is a dictionary. But you can put in a Gensim dictionary object. You can also put in any dictionary which has IDs and words, but the idea is 0 to whatever. And the reason, again, is because when you print your topics, it needs to have an ID to word mapping. So it's just for Gensim to know what's going on, right? Any questions before that? No? OK, cool. So I'm going to run this. It's not a super massive corpus, right? It's only 300 documents, and normally that's tiny data in the context of data analysis. Normally you're dealing with thousands of documents, but for the purpose of this tutorial, but 300 is still a reasonable number. So I'd like to make it very clear, the more documents you have, the more fleshed out your topics are going to look, right? 300 documents is not enough to have really beautiful topics come up which represent some kind of complexity. But that being said, let's see what kind of topics we have. OK, People Day, Australia, Australian. Oh, this is an Australian day maybe. And Adelaide Airline, then you have your company, then you have something with the Taliban. Australian Kill Force Company, it's pretty, 2001 was not. Well, yeah, so you have, these are the topics which you see, so you can see there's a kind of a theme going on. There's something, government, Pakistan, India, attack, force. So, well, there's a bunch of different topics. You can really fine tune. This is 10. I could totally do like 5, run this again. In the meantime, you could just have a look. Tell you what this looked like. 0 is topic 0, topic 1, topic 2. So also the topic which I've called like the weather topic or the sports topic, it won't exist, like it won't have a title. You have to give each topic a title of your own. A topic is a probabilistic distribution of words, right? So it's like these words are going to appear in this topic with that, the odds of these words appearing in the topic are more. So I'm just going to show you with 5 topics what it looks like. Maybe it's a bit better. people police task force, one in Australia. So you can see over here, maybe Australia is not a very important word because it's an Australian newspaper corpus. We don't maybe need that. You could then add that in your stop words, remove it, and do it again, and then you'd see your results, right? So you can see it's a heavily iterative process of finding out your ideal topics. Again, my topic modeling tutorial in the same repository goes into more details on getting better topic models, right? This is just to give you an idea of what they look like and what you can do. Also, based on your data set, it'll be varyingly useful or not useful at all. It's kind of hit and miss, but I find it very useful in exploring large textual data sets. You could also find out the percentage of each topic in different documents. It's just a useful model of your textual data if it's unclassified, in my opinion.
Question?
Yeah?
How do you decide how many topics to use?
That's a very good question. Now, I did mention about how I do have a topic modeling tutorial, which I'm going to briefly open but not get into. It's called topic modeling. So over here, I actually talk about how to find the number of topics well, one way, which I'm going to very, very briefly get into, is something called topic coherence, which is a quantitative way to tell you how good or bad your topic is. So what you would do is you would run your topic model for 7, 8, 9, 10, or 10, 15, 20, whatever, whatever you think might be the number of topics. Check out the topic coherence values for each of these topics, for number of topics, and then choose the best number. The other way is it's a really tough question. There are different ways you can find out how good a topic model is, but in the end, it really comes down to this looks kind of right, But that being said, there are a few quantitative ways. Topic coherence is one of these ways. There's also a bunch of pretty graphs and plots which allow you to kind of figure out, like for example, one way is this is one way. You can see over here. This is not in this tutorial, but a different one, which you can see. You can see a lot of these. These are all topics, by the way. This is a visualization of topics. You can see that a lot of these topics are clustering together. So hey, why not just have one topic instead of all of those, right? So these are ways you can try and figure out optimize your topic model, so to say. But we're not going to be getting into that. It is super interesting still, I think, just to be able to find out what kind of topics are in your text with like no prior information. To be clear, there was no classification going on over here. We gave no information. We just threw like a bunch of text and it said this is useful information, which I think is very, very cool. So I'm a big fan of topic models, and I think they're really useful and interesting. Yeah?
So for the coefficient in front of the numbers like 0.005 and 0.004, is that the probability or is that a correlation of certain strength?
It is the probability of that word appearing in that topic. We only show the top 10. I believe it's 10. You can choose that, by the way. Gensum allows you to choose the number of top words in a topic you want to display. In this case, it basically says, for these 5 topics, these are the 10 most probable words to appear in that topic. So these words tend to aggregate over here, you see? Now, as you'd go on, you'd have obviously like the probability gets lower and lower and lower. And also, this probability is shared between 5,239 words, right? So you may argue, oh, 0.004 is a tiny, but it's not in the context, right? So you'd also have more interesting results the larger your data set. And Gensum is a really neat package which does a lot of different kinds of topic models. This is not the only kind. There's a lot of different kinds of topic models, by the way. Yeah?
I was wondering what the stemming part, you ran it before, but for example, here we see Australia.
Sure, sure. So I think in this particular case, in this kind of stemming, I think because it's a proper noun, it's ignored. That would be my guess, right? Yeah, that would be my guess. Normally this would be caught though. That's a good point. Again, like all of these kind of things, like every time I do like a variant of this tutorial or this tutorial, people point out that, hey, this is kind of, and that happens, and that's awesome. That just goes to kind of prove my point that you need to do multiple iterations to get very useful results. The text cleaning part, like a lot of the text cleaning happens after you finish the project, right? Because you're doing it the second time to get better results. So that's something where cool that you pointed out. Yeah, so Australia and Australian, you'd argue that it might not be stemming or stemming. So what I would do is I would tell my Spacey model, which on the Spacey website you can see how you do this, right? You can tell the model to make exceptions and catch these things and fine tune your stuff. But yeah, that's a good point. So is everyone kind of clear with what topic models are? Are there more questions about topic models? I wouldn't mind talking about topic models a little bit more, but you could also, there's other tutorials in the same repository you can get into more details about. But that's the general idea of topic models, and these are one of the things you can do with text. Now, I'm going to move on to text classification. So now we're going to stop using, yeah.
So when you're converting it to a bag of words architecture, how are you preserving the context of the word?
Oh, that's a very good question. So the question is, how are you preserving the context of the words when you're converting into bag of words? You are not. You are throwing context out the window. That's 100%. So there are, depending on what you, so the thing about topic modeling, right, for example, or text classification, we don't care so much so about the context of the words as we care about the presence of these words. Like in spam and not spam, like a popular thing, like if you have like lottery, prize, winner, so on and so forth, just the words that they exist is a big giveaway. It's not the most sophisticated way because you're certainly losing context, 100%. And if you want even better classification, which has context, there are ways, there's something called word-to-vec, which is a way you preserve context, which is also really popularly used in text analysis. I might briefly talk about it later, if you have the time. So there are methods you can use to preserve context. It really depends on the kind of project or problem you want to solve. But yeah, bag of words, and even this original way, it only lets you know if that word exists in that document. If you want to know the way sentences are structured, semantic meaning, or contextual understanding, you have more interesting machine learning algorithms which allow you to do this. And I will actually be very briefly talking about them. And they are now leading the forefront of textual classification. All these things are done using these context-based models which capture this. But for the longest time, we didn't have context. 2013 or 15 was when word-to-vec came up. I mean, people are trying to solve this context problem for a while. The most sophisticated way was word-to-vec, which is done by some folks over at Google, where they tried to capture this context which you talk about. And you can later do this as well. But for this talk, we're going to be sticking to this. But that is a very good question. And if you have more to, you should definitely read about it. Just talk to me about it after this. I would love to. Yeah?
You can tell me that this is not the talk. But have you looked at LDA yet?
Yeah, LD2Vec is
like-
super cool.
like
Yeah.
Last year or this year?
Yeah, it's very recent. Some Jensen are trying to get that into their package as well. No, I totally dig LDA2Vec. It's awesome. But that's, so these are other statistical learning algorithms which also use topic models as part of this context. I mean, there's a lot of things, and the whole point of this tutorial is to also just kind of introduce everyone to that, and then you can go into more details if you'd like. So I will talk about all of this towards the end, but now I'm going to move on to text classification. Are there any other questions before that? Is that it? Okay. Cool. So so far we worked with unlabeled, unstructured data, right? Like we got the data dump of newspaper articles. There was we didn't know what that was going to be about. I mean, I knew because I saw it, but the computer had no clue about what it's going to be about. Now we're going to be dealing with data which is already classified. When you know, for example, I mean, there was an interesting project which I was trying to work on before with a bunch of people back at my university where we're looking at if we can predict if someone has early signs of depression based on looking at their social media posts. And this is a particular example where text analysis is super handy, right? So I had data where I knew where certain updates or posts were like ranked as how depressive they are, so to say. And based on that, I was supposed to tell how depressive or non-depressive other social media posts. Again, this is just one context. It could be literally anything, right? So in this case, we classify our data before, or we annotate our data before. Annotating or classifying basically, annotating actually basically means when you're part of speech tagging is also a part of a kind of annotation. It's when you tell your data what it is before you do any kind of classification task. When you mark it, label, or annotate it, the computer knows, your machine learning algorithm knows what kind of data labels you're dealing with. It's just also called labeling your data. So we're going to be looking at now problems where we have labels on our data. And usually when you're lucky, you have some kind of labels. You want to get a percentage of accuracy. So this is called classification problems or supervised learning. Supervised because you're giving labels or annotations. What we did before was unsupervised because we didn't really, apart from the number of topics, but it's still called unsupervised, and this is called supervised. Now, I'm going to be going over this part a lot faster because it's the idea It's just to, again, let you know what's available, right? If you want me to slow down, though, please let me know, and I will go slow, but it's also the last 25 minutes, so I'm going to kind of up the pace over here. So a bunch of imports over here. All these imports are to get our data set ready, and we're going to be using scikit-learn now. And we're going to I'm moving away from GenSim and going to scikit-learn because scikit-learn is very popular in machine learning, and it also has a lot of cool tech stuff, which is what I want to introduce everyone to. So I'm going to do some things for feature extraction, which is TF, ID, vector, blah, blah, a bunch of imports. Basically, a lot of imports, but we need these, and I will explain why. Now what I'm going to be doing in this particular cell is data transformations and getting my data. Now, what I talked about, we're going to be also switching data sets, so we're going out of our Australian newspaper corpus, right? So now we're going to be using something called a 20NG data set, or 20 newsgroups data set. There are 20 categories. We're only going to be using 4 of these 20 categories, which are, these are random, but 2 of them are about religion, 1 is on graphics, 1 is space. I just picked the first 4, I think. So we're not going to be doing classification for all 20. We're going to be doing 4. That's again for this particular example. You would have complex tasks with 20 or even more labels. For this one, we're just using 4 because it's faster. So data train. So in these kind of cases, you are training a model which you are then using to predict, right? That's a kind of different kind of paradigm than what we dealt with before. Previously, we were just kind of getting information about our data. Now we're going to actually train a machine learning model based on what we saw and classify into a particular class based on that model. If any of these words are not making sense, stop me, but I will explain them in a wee bit. So you have data train, which is a variable. So fetch 20 news groups, basically fetch this data, which is just a function by scikit-learn. The subset is only trained, so I'm only getting my training data. Training data is labeled data, right? That's very important. Any kind of data which you're using to train a model on is already has labels or annotations. We're going to be learning from these annotations and this data to make new predictions or new labels for unseen documents. So now the other thing, so I previously talked about bag of words, right? And that's one way to represent your textual data. Now we're going to be, that was also kind of manual where we kind of created that using GenSim. Now I'm going to show you how scikit-learn does this. So now I'm going to say I don't want a bag of words. I want to make it even more sparse. I want to use 5, in this case 5, I mean, I just chose 5, it could be anything, right? So again, we have a vocabulary. Last case was 5,300 and something. This time it would probably be around that as well. I don't want to use the entire vocabulary. I want to train it on a smaller part of it. So I'm going to, here the number of components is 5. And I'm basically transforming my data. Now, what does this mean? Previously, we also did this actually. When we transformed our data from our raw textual data to our bag of words, and this part, what I showed you before. Now we're going to be transforming our data into something called TF-IDF, which stands for Term Frequency Inverse Document Frequency, is what it stands for. The idea is you want to get words which are appearing a whole lot of times in a lot of documents, but not in every document, so it's called inverse document. I'm not going to get into the math part of it right now. If you are interested, again, like you can search it up. It's really popular in text analysis term. It's basically like bag of words. It's a way of representing your textual data. So that's why you have TF-IDF vectorizer, training and transforming. Now, even after I do this, there's still a lot of words in my vocabulary. So now what I want to do is I want to reduce the number of dimensions. There's a lot of ways you can reduce the number of dimensions of something. This just means 10,000 dimensions over here. I want to reduce that to 4 or 5 or something which is easier for a computer to understand. Here that's SVD, or it's called. So SVD is basically a vector decomposition, singular vector. So it's a kind of decomposition where you have a massive matrix. Now all of these, when you have a lot of documents, becomes a really massive matrix, right? When you want to reduce this to a small number of dimensions, use different kinds of machine learning or linear algebra methods to do this. One way is SVD. So SVD, so these are, again, I just want to introduce you all to different ways in which you can normalize your data or basically make a huge vocabulary smaller. So what we're doing now is we are, so LSAs, latent semantic analysis, all of these are basically, the idea is have a lot of words. A lot of words are going to be kind of complicated in classification. So let's lower our dimensions into something we can use better. And in this case, it's TF, IDF, and SVD. I also want to just kind of throw a lot of words at you all, so you can later go and Google it and then be like, wow, I learned all this cool stuff. And but the idea is to lower your number of dimensions. That is the core idea of this. The reason why we do it is, again, like I talked about before, these are a lot of dimensions. Here, dimensions is the features. Dimensions are basically the number of things you are using to make a prediction or train a model, right? Now I'm doing the same thing, but I'm doing it for my testing data. Before this, it was my training data. Remember, we have classification now, which means it's supervised, which means we have training and testing and things like this, which we did not have before with topic models. So we create our model by training on certain kind of data, and then we see how good this model is by testing it on test data, right? So you can see over here, like, so scikit-learn offers, I'm sorry, I didn't run this. Panic there for a bit. There we go. So that happened really fast. Also, scikit-learn offers really nice tutorials on what exactly is going on within this. It's out of the context for me to talk, out of the context of this tutorial, for me to talk about how exactly the data reduction, dimension reduction is going on. I would really recommend Googling it and finding out more about it, because it's a pretty important idea. But since we're sticking to text analysis, I'm going to move on. So now we created our training, our testing set. Again, these two cells have a lot of code. Take your time to go through it and the documentation later, so you know what exactly is going on. What you need to know is a lot of dimensions, less dimensions, data is not ready. So what exactly are we doing? There are many different kinds of machine learning algorithms which we can use to classify data. What we used before, topic models, are also a suite of probabilistic or machine learning models, but that was not classification. Classification, like I said before, you know a label, you make a prediction, like the spam and not spam thing. Even for spam and not spam, the earliest spam identification models were usually something called Gaussian naive Bayes, which is basically a classification. It's a classification algorithm where it looks at, oh, these kind of words end up appearing in a lot of mails which have spam, so these kind of words are probably more spammy words. So that's how it does it under the hood, right? In a probabilistic manner by looking at each word and adjusting these probabilities. We're just going to do import Gaussian NB, which makes our life a lot easier. And we train these models. Now, I've done GNB is equal to Gaussian NB, which is our model. Then I've done GNB.fit xtrain ytrain dot predict. What exactly is going on? I am fitting my model. This could also be in 2 lines. I'm just doing it in 1 line over here. But I'm fitting my model using my xtrain and ytrain. Xtrain is my data. Ytrain is the label for the data. I've talked about labels before. And now, once I fit my model, here fit is training. I'm now creating my model. And once I'm done training or fitting my model, it's fit because it fits it according to the probabilistic thing, right? And then after that, it's predict, which means I'm making a prediction on X test, which is my testing data. So ypred NB would be the prediction which my machine learning model has made on the test data. And you can see it says 0, 3. And why does it say that? It basically says, OK, let's just look at the first document. So the first document was, which in the text, in our test data, was classified into class 0. Do you see? So based on the contents of what was our first test file, it was placed over there. And 3 is our 4th class, and the 22nd document was put in our 4th class, and so on and so forth. So now what you've done is you have X test, which is all of your testing data, which we didn't know what class this was, right? We are now using this model to classify this test data into one of these 4 classes, which is what has happened over here. Classification is not limited to only text, by the way. The same methods I've used before, like TF-IDF, is particularly for text because it's term frequency. But you also do image classification, right? That's like a super common task where you have handwritten, like your handwriting from 0 to 9, and you want to see every single handwritten 0 to 9, if what does the computer call it? That's also classification. It's just the labels and classes are different in a different context. But classification is a generic machine learning problem. In the context of text classification, what just happened was I had a document which is either about atheism, religion, graphics, or space, and it was classified into one of these 4 based on the contents of that document, right? Everyone cool with classification, more or less? So here we use scikit-learn to do it. Scikit-learn has pretty much the same kind of pipeline for all classification tasks. So this kind of teaches you how to do classification for other contexts as well. But in text, you'd use TF-IDF and all these things over here. So GenSim and scikit-learn are kind of different in that context of the kind of problems you want to solve and the way you want to do it. But they're both fairly easy, and you can kind of use the same corpus in both places. It's pretty cool. SVC is something called support vector classifier, where support vector machines are another kind of machine learning algorithm where you try to create a plane instead of classifying by a line. Use a plane instead. Yeah.
Yeah. In TF-IDF, I can see a bunch of parameters for document frequency and IDF.
Sure.
That I understand. But how does it consider like TF part? Because we have multiple documents.
Sure.
That, like term frequency is attached with each document, right?
Sure.
So how does it make a single vector for all the throughout the corpus? Like how does
so I'd actually have to be absolutely honest. So the question was basically how does the scikit-learn TF-IDF vectorizer find the term frequencies for all the documents?
Yes.
Correct. So I'm not sure how scikit-learn does this under the hood. I would have to go and double check, and then maybe we can look at it later. I'm not sure. I'm not actually 100% sure how it does it under the hood, but it does seem to do the job because this particular module, right, is for text analysis, like the TF-IDF part. So the way they've set it up is such that it takes care of this. But I'm not sure exactly how. I'd have to look at the code or look at the parameters and see what's going on. But it's a good thing you pointed out because you can also look at the other parameters which are part of that, which says stopwords is English. We did the stopwords bit a bit more manually before. Here scikit-learn does the stopwords as part of it, but also means you cannot play around with the stopwords as much. So there's there's certain levels. Use IDF, true or false, then the maximum document frequency, minimum. So these are the standard values which I picked up off scikit-learn. You can really play around with it. Again, to be clear, TF-IDF, term frequency, inverse document frequency, different way of representing our textual documents, similar to bag of words that we used before, but a little more nuanced. And you don't have to use it. It's just useful, and you can do cool things with it and represent your data better. To answer your question in particular, we'd have to go over the scikit-learn documentation and figure it out. I don't want to give a wrong answer, which I'm not 100% sure about. But we can definitely talk about it. Cool. So we are at the last part of the tutorial. I will be going over this part a little faster because there are 12 minutes left, and I want to give at least 5 to 7 minutes for questions. If we don't have questions, then I can do this in more detail. But I'm going to go really fast into this. So deep learning is a subfield of machine learning. I don't think I really introduced what machine learning is. Machine learning is basically a lot of data, then you put it inside a usually statistical or an iterative algorithm which learns from data and makes prediction. That is a general idea, which we've been doing before this as well, right? So deep learning. Deep learning it's called deep learning because we use something called deep neural networks. There's also something called shallow learning, by the way, when we just use like a neural network with just 1 or 2 layers. The reason it's called deep is because you use multiple layers. The more layers you have, the deeper your network is. And in general, deep learning largely like all these kinds of neural networks which have over like an arbitrary number of networks, like 8, you would say layers, would all be deep learning networks. Pardon me. There are many kinds of deep learning networks or neural networks in general. There are a lot of different kinds of neural networks. Neural networks are kind of like, they are a mathematical construct which is kind of modeled after a human brain more or less in the way it passes information between different nodes. I will not get into details of what a neural network is because again that is like a huge talk of its own. What you would know is these are more powerful, computationally intensive class of machine learning algorithms which are loosely modeled on the biological brain is a very brief idea of what they are. There are many different kinds of neural networks. What we will be using is something called recurrent neural networks, which are kind of like stacked in a way where the data is recurrent. And in particular, we'll be using something called LSTM, which stands for long short-term memory, which is a way because memory is important because you have to remember context. Someone asked me about context before. So neural networks are really good at capturing context. Someone also mentioned LDA to vec, which stands for LDA to vector, or word to vector. These are all things I've said before. All of these are really useful in understanding context because they have memory, so to say, in terms of how they learn these models. So they're more sophisticated, more intensive, and really cool, actually. I've put up a lot of links over here, and I would really, really recommend reading these links because it's an excellent blog post over there, these 2 links. I would also, any word you don't understand in this tutorial, just Google it. There's a lot of really nice resources, or mail me, or raise an issue on my repository, and I could direct you to some interesting reading material about these things. Now, what we're going to be using is this machine learning model to learn text. The way it happens, I'm going to kind of be a little fast about this, but the general idea is this neural network learns based on the context of one particular character, what is the most likely character on either side. Now, you extend this to words and so on and so forth. So what does this mean? It means I am most likely, personally, I am most likely, if I'm going to be talking about myself, for example, like in this context, I would start a sentence with I, right? So neural network starts to learn these things, that you start sentences with I, or he, or she, or they, or whatever. It learns these things. And it learns after a particular word, what is the most likely, like after deep, I'm probably going to have fried after that. I mean, it's just going to learn different kinds of things based on the context, based on the data you're training it on. It could be drastically different. But what it learns is, what is the most likely character or word after this particular character word I already have? That's what it's going to do. Now, how is this cool? You can pretty much teach a neural network to talk like Shakespeare. If you give a whole bunch of, like, not a whole, like every single play written by Shakespeare, which is also an example given in this blog post. If you give every single Shakespeare play, this computer would learn that, this neural network would learn that in the context of Shakespeare plays, after thou, the most likely word would be hast or whatever, you know? So it's really cool. It learns the most likely word. What this means is it learns English or Spanish or whatever you're teaching it. It doesn't really know what's going on, but it knows what's the most likely thing to happen. Now, I've told you about this, and I never have the time to get into the details of how to do this, but I always still have this code over here because it's useful. Let's go super, super fast. There's like 5 minutes left. So what's going on over here is this is just my imports. This is just, remember I talked about like how data is stored. This is called one-hot encoding, where you have one yes and then all of these. Here's just to show you the kind of data which neural networks take in as inputs. Now, so a lot of the parts is these neural networks are very complex in the way they're made, right? But there are lots of tutorials which tell you how to make these neural networks. You don't make them from scratch. This is one way. So you have like a hidden dimension. Then you have what the drop rate, activation, softmax. All of these are the characteristics of these neural networks. Softmax is a kind of activation. Then you have drop rate, which is at what point do you stop overfitting. So these are a lot of things which are particular to neural networks, and this is how we're creating our model. So I'm just running these 3 functions. So over here you have certain characteristics of these neural networks, which again I do not possibly have the time to explain it to you, but I would really recommend going in and finding out what exactly they do, because depending on how you want to keep these parameters, the way your neural network learns things are very different. Neural networks also take a very long time to actually train, like hours, days to train, depending on how big it is, right? So all this code over here will take you, you don't need to really pay too much attention to it right now. This is for you all to try out when you're home or wherever. So this is what we're going to be doing to get our models. This is how we train it. And now what I told you before is I generate text, right? So this is now our model, the code, the functions are done for training the model. This is how I'm going to generate my model. It's basically really, really fast, right? I start with a random seed, and then after that, I basically say, based on the current word, I make a prediction of based on the current character, not even, this is a character level learning model. There's also a word-based learning model, right? This is actually learned words on its own, not just, it's learned how to make words, not just what comes afterwards. It's a pretty complex model. So what's happening over here is based on the previous word, I'm going to make based on the previous character, I'm going to make a prediction of what the next character is. And it does that, and I'm going to be using the Lee background corpus. I had this Game of Thrones corpus, just cool, but it was totally legal. So I'm going to actually You never saw that. So I'm going to go back and use the newspaper corpus, which we were talking about before. And these are all my unique characters and mapping, and bam, bam, running a lot of code. I'm sorry, I'm so bad for doing this. But basically, the point is what's happened over here is I've used all of that newspaper article corpus to kind of teach this model of what exactly did newspaper articles look like in the 2000s, and it's going to do that. Now, it's going to take some time to load because it takes some, but I want to very, very briefly show you some of, like, what I've done is, what you've seen is the actual code of how to do this yourself in this blog post, which I've linked to. This over here, this is Shakespeare written by a neural network. This is not a human being. This is a neural network which has done this. I would have loved to show you Shakespeare data myself, but it takes a lot of time to train these models. So this is an example from the blog post which I've linked to. It has learned how to write code. It can do latex. It's pretty nuts. You can do a lot of very cool things. About how useful it is, I'm not always 100% sure, but it's still very interesting, and it could possibly have some business. I'm a researcher, so I can just do things for fun and not really care about how it's useful in the real world. But this is one of the cool things you can also do. So that's pretty much what the tutorial is. I'm sorry for running through the last bit of it. I usually end up always doing that, but I want to include this in the tutorial. You can have the code and look at it in more detail. So this is everything we've talked about. It was quite a lot, I understand. It was kind of fast and didn't let you do the stuff on your own. But I do hope that you would download all of these packages, set up your environment, and be able to do all these things and understand why you're doing all these things back whenever you get more time. And thanks a lot for listening. I'm also here tomorrow and on Tuesday. I'm speaking tomorrow where I will be, I usually talk about this tutorial kind of in my talk. So I'll be talking about text analysis and the kind of things you can do. So if you want to know a little bit more, you can listen to me. I'm also easily contactable on GitHub, Gmail, whatever. I'd love to get questions or anything you'd like to ask me about text analysis. And thank you very much.